Hello, hi ISAs. Dr. Bowers here. This is such a strange lab. I never have this much difficulty getting something organized, but it's all because we decided to skip all of the quadratics because we thought that, students coming from 105 would know this material, but I don't know if they do or not. So I'm kind of sending you out there with this lab that won't be that fun, and there's not really, because we don't even get to the fun of doing the cube root, because we just want to make sure that they understand how to graph complex numbers and what they are. So my goal is that you'll start out with the warm-up and maybe try something new. Greet them at the door with the handout. So you're going to be asking them to do these 6 questions. Oh my god, I have 2 5s. I'll fix that. But the idea is that you're going to try to just practice different applications with multiplying, subtracting, adding, and dividing. Implicit message here is that imaginary numbers are simply numbers, just like integers or fractions. So again, the elephant, basically trying to get at this idea that just because you know how to do these individual skills doesn't mean that you're getting the idea of complex numbers. So the more we can try to bring it together by looking at all these different ideas, the more you can understand and appreciate the real beauty of complex numbers. So I'm thinking that slide 4 should only take you about half a minute. I think the warm-up should take you about 10 minutes, if that, but by the time everybody shows up and everything and gets ready and gets settled. So you're going to start off with talking about the goals. And so factors of a quadratic, they've done that in lecture, but we're just going to expand it to complex. Graphing in a complex plane, they have not done. That's something new. Zeros of a quadratic, they probably have, but again, pulling it all together. Equation for the vertex and the value of the discriminant. So when you do the warm-up for slide 5, I'm assuming this is only going to take you about 2 minutes. I don't want you to review all of them. Don't go over all of them. Just say, I'm going to put the answers up here. If you have any questions, talk with your neighbor. If your neighbor also isn't sure, then call me over. But just give them about 2 minutes or so. Feel it out. See how long it will take. But I can't imagine it'll take too long because they should know this. So part 2 is graphing, and then what we're going to do is have them graph all these values that they just computed. So in this case now, there's 3 things that I'd like you to emphasize on slide 6. Number 1 is complex numbers are always written in the form of a plus bi, and you do want to separate the fractions, not just because that's the way you enter them in my math lab, but because there really is a real part and an imaginary part. And if you put them all together, then you can't really graph them and figure out which is the real part and which is the imaginary part. The second point is that all real numbers are also complex numbers because they're just of the form a plus 0i, and they just lie on the real axis here. And the third is that a lot of people think that this imaginary axis and the real axis is the same thing as the Cartesian plane. It's not. These are not. This is the x-axis, but this is not the y-axis. And the imaginary part is not, a function of the real part. It's just like 2 parts of a number. It's like saying that 12 is 10 plus 2. There's no relation between the 10 and the 2 other than that one is the 10s and one is the 1s. So it's sort of is similar to that. Okay, slides 7 and 8, I'm assuming you're going to spend about 2 minutes total on this. But what I want you to do is give them time to plot those points. So the first one is done, the 0 plus negative I. It would be 0 comma negative 1, which you can show them is down here. And then just tell them to go ahead and do the rest of them. And you can walk around and see how they're doing. I'm assuming this wouldn't be too bad, but you might want to get 1 or 2 students up on the board to show you where they would be. The next slide here has an animation of all of them. You can either do them individually or you can put them just all up and just show them on the board. And again, have students compare their worksheet with what yours showing up at the top of the board and see if they get it right. Okay? So that's, where am I here for time? Okay, so the next thing is slide 9. This is a big one. slide 9 is working backwards. So the idea here is that first you're just going to say that, just like in class, if you are given 1 0 n, then the factor is x minus n. If you're given 2 zeros n and m, then the function is the product of these two factors, x minus n and x minus m. So on their worksheet on part 3, they're given two examples. One is 2i and negative 2i. So the roots are x minus 2i and x minus negative 2i. And the other one is 3 plus 2i and 3 minus 2i. So given these two, give them about 2 minutes. Well, maybe even, I have up to 10 minutes on my slide here, but to have them work out what the functions are given those two roots. And here you can walk around and find two people who get the right answer. You can tell them it's the right answer and say, would you mind putting it on the board? That saves you time because you don't have to put it on the board, but it's on the board, and have them each present it. And they'll be okay with that because you already told them that their answer is right. So that should take maybe 10 minutes. Okay. And then you can show the answer. This is really just for you because hopefully they'll have the right answers on the board. All right, so then the wonderful bounty of the quadratic formula. What I want to show here is there's two parts that are important to us. One is the negative b over 2a gives you the x-coordinate of the vertex. And then this part here is called the discriminant, and it tells you the nature of the zeros of the parabola. Now, maybe some teachers would stop here and say, okay, just, let's just memorize this, but I'm not going to do that. So when we look at the x-coordinate is negative b over 2a, and then you put that back in the function to get the y-coordinate of the vertex. So if you have this here, x squared minus x minus 6, that's factored to x minus 3 times x plus 2. And so I want to say negative b, which is negative of negative 1, which is going to be 1 divided by 2 times 1, which is 2. So your x-coordinate is a half. And then I just think it's easier to stick it in here, right? You get a half minus 3 is negative 2.5. And then a half plus 2 is 2.5. And you get negative 5 halves times 5 halves, or 25 fourths. Okay, let's see. That should be negative 25 fourths, shouldn't it? Yeah, that should be negative 25 fourths. I'll fix that. All right, so now we're going to get into the rules here. I've seen that people just write this down. If the discriminant is positive, you have 2 real roots. If the discriminant is 0, you have 1. If the discriminant is negative, less than 0, you have 0 real roots. What I want you to do on slide 12 is to give them about 2 minutes to just think about why do these rules hold. Just reinforcing that idea that we want to think about these things. They can talk to a neighbor, or they can just think about it themselves. And then you can ask for volunteers and listen to their answers. Hopefully they say something along the lines of the x-coordinate, the negative b over 2a, but the discriminant part, right, is b squared minus 4ac. So if the value under this radical here is really the red part that we're looking at, right? So if this is a positive number, then the square root of a positive number is a positive number. So it's a real two real roots because you have plus or minus. If the discriminant is 0, that means you have plus or minus 0, so you have 1 real root. And if the discriminant is negative, that means you have plus or minus 2 imaginary roots. And you also want to emphasize that the plus or minus, the negative b over 2a is the x-coordinate of the vertex, and then plus or minus this discriminant shows that the 2 roots are symmetric about the vertex. All right, so that was slide 13, and that should hopefully take just about a minute. Again, what you want to do is listen to their answers and try to hear the good terminology, not just it or normally or things like that. You want to, what do you mean by normal? What do you mean by there's 2 roots? Why are there 2 roots? But just often you don't even have to say, what do you mean by? Just say, can you clarify? Or did someone else want to restate what that person just said? That's ideal. It doesn't always work that way. I certainly don't always get people to talk at all. All right, slide 14. This is the main part of the lab, and I cut it down. I used to have 4 here. Now I just have 3 equations because it does go over everything. So what's the vertex? What's the value of the discriminant? Oops. What are the real or complex zeros? And what are the zeros of, what are they? Are they real or complex, and what are they? And then what are the factors? So hopefully this will pull it all together, all of the kinds of things that we were talking about. So this first answer here, when you get the negative b over 2a, you end up with 1/2. It's minus a negative 1 over 2, so that's 1/2. And when you put 1/2 into the formula, you get negative 5/2 times 5/2, which is negative 25/4, or negative 6 1/4. The discriminant is just the value of b squared minus 4ac. So in this case, it's 1 minus negative 24, which is 25. So the discriminant is greater than 0. So we know that there's 2 real roots. We also know that since this vertex is 1/2 negative 25/4, that's below the x-axis, and the leading coefficient here is positive, so the end behavior goes up. So we know that there is going to be 2 real roots because the vertex is underneath the y-axis. So the 2 roots are negative 2 and 3. You could either get that by factoring or by using the quadratic equation, and here's the factorization. So again, you want to point out that these are the 2 real roots. In the second case, when you do the negative b over 2a, you get 1, right? Because you're going to get negative 2 over 2, which is 1. And I can put 1 in here. I get 1 minus 2 is negative 1 plus 3 is 2. So the vertex is 1, 2. Then you do the discriminant. You're going to get here 4 minus 12, which is negative 8. So the discriminant is less than 0. So there's 2 complex roots. And here they are using the quadratic formula, and the work is here. And so your factors are x minus that times x minus this and x minus that. This is a little bit complicated, so hopefully you'll be able to find 3 students, each of whom got these right, and will be able to put them on the board. It's much better to have them put it on the board and you watch, walk over and listen to the way that they present, rather than you doing everything at the board. And the final one is the same idea. The equation, the vertex stands at negative 1, 3. And since the discriminant is negative, you know that the end behavior is positive. Negative 1, 3 is above the x-axis here. And here are the 2 roots, negative 1 plus I root 3 and negative 1 minus I root 3. So those are the factors. So again, you want to emphasize the difference between the zeros and the factors. Basically, we use zeros and roots interchangeably. Sometimes the book uses the word zeros. We actually Googled the difference between root and 0, and we couldn't honestly figure it out. There is a difference between x-intercept and 0. Obviously, an x-intercept would be a real root, whereas x-intercept does not apply for complex numbers. So that's it. The last thing is just to say, well, if this thing is floating in space, this turns out to be this one here. If this is floating in space, then where are the zeros? And again, we know they're right here, just plotting them on the complex plane. So just call attention to the fact that the complex plane is not the same as the Cartesian plane. Here's the function. And what's interesting too is to notice that even though there's no real roots, all roots are going to be symmetric about the x-coordinate of the vertex. So here the x-coordinate of the vertex is the 1, the 1 plus root 3 and 1 minus I root 3. So you can see they're symmetric here about the real part of the roots, or of the zeros. Okay. So that is an extra bonus. If they notice that, that's really neat. And again, you can see the symmetry here with the x-coordinate of the vertex, but here they're symmetric about just about the real part, and this is where you get your plus and your minus. So they're only symmetric about the real part of the x, or about the zeros. So hopefully this will only take you about, well, it should take you about 10 minutes to do the main part of the assignment, about 5 minutes to go over it, hopefully with your student presenters. And that's it. I took away the reflection questions, so this is the end of the lab. So hopefully this won't take you too long. Don't worry if you don't get through it. Do the best you can. Thanks a lot.